So when we looked at our lab data, you had acceleration on the vertical axis, and you had the net force, or the unbalanced force, on the horizontal axis. Your acceleration was measured in meters per second squared, and your force was measured in newtons. And you plotted accelerations and forces, and hopefully you got something that looked about like this. And then we created a best fit straight line and an equation for that line, which looked like something like acceleration was equal to slope value, some number, times force plus some intercept. And we discussed how the intercept was kind of a strange thing, because if there's zero force, then there should be zero acceleration, and that the intercept may indicate some uncertainty in our measurements or our equipment. Maybe we didn't start out with a completely flat surface to begin with, because the little carts have some friction in the wheels that would keep them from rolling on the track. So there was some error or uncertainty in the equipment. Plus, you had to, the force sensors are so sensitive that they bounced around quite a bit, and you had to like kind of pick the middle force or so. So you may have picked slightly larger or slightly smaller forces and ended up with a intercept. After we analyzed the value of our slope, we found that that slope meant 1 over the mass of the cart. So that means that acceleration is equal to the net force, the sigma symbol means net, the net force divided by the total mass. And that's how the Newton's second law is written on the equation sheet for AP Physics 1. It's not my favorite thing in the world, because we don't use that version that often. Most of the time, you're going to use that the net force is equal to MA. So the net force the mass that the net force is acting on, and then this A represents the acceleration of the mass. So now, how do we use this? Alright, so let's apply this. I'm going to do a couple of examples with you so you'll know how to use this whole net force thing. So let's say, for example, that's not a sigma, that's supposed to be an E. So let me make an example here. Alright, let's say we have a 2 kilogram block is pushed with a force of 4 newtons along a flat surface with a coefficient of friction of 0.1. So what we're going to do first is we're going to draw the Freebody diagram. We're going to sum the forces, and then we're going to determine the acceleration. Okay, so what does this look like? There's a flat surface, and we got just a block, just something like that sitting there, and then we've got a force acting on it. This force push. Okay, so that's like the picture. My 2 kilogram object. You've got a rough surface here, so if you want to put some zigzags on there to make it look all rough and ugly, that's cool. All right. Whoops. Sorry about that. So now the free body diagram would look like, here's my little object, and we're pushing on it to the right. So all vector forces start on the body and are drawn away from the body. So force push to the right. There's a weight force on it because it's on the face of the planet Earth. There's a normal force on it because it's sitting on a flat surface here. And then there's a friction force. And I'm actually going to draw the friction force coming out of the bottom like that so that it just really looks like it's along that surface there. So sometimes drawing the forces from where they start kind of help remind you what they are and what they do. Okay? Then we're going to sum the forces. So when I sum the forces in the x direction, I want to set them equal to m times a. Because I'm looking for the acceleration. Now if my answer turns out to be 0, then that means the acceleration is 0, so the speed is constant. Okay, so maybe this block is just sliding along this. You've got enough push to counteract the frictional kinetic force, and it just moves along. Okay? Maybe the acceleration is negative. That would tell me that there's so much friction that this push is not enough and it's slowing down. If the acceleration is positive, then I know that my push is bigger than the force of friction and it's speeding up. There's a lot of things kind of embedded in the meaning of that acceleration. So in the x direction, you've got force push minus force friction, kinetic, is equal to ma. Now in the y direction, it's just not moving up or down. It's not in the elevator, it's not on an escalator or some forklift that's, raising it up. So the forces in the y direction are balanced. It's not moving in the y direction. So then the normal force is up, the weight force is down, and I set them equal to 0. Now I want to find this acceleration. I know the mass, I know the push force, so I got to figure out what is the force of friction. So force push minus, now I learned that the force of friction, we determined this through our lab, was the coefficient of kinetic friction times the normal force, and that would be equal to ma. Now the normal force I can solve for up here. So the normal force is equal to the gravitational force, and the gravitational force is equal to mass times the gravitational field of the planet that you're on. It's like a big substitution party. So then you'll have force push minus mu k times m times g equals m times a. I made a substitution, this up in here for that guy. That takes him down to there. So far so good? All right. Now, that means that force push minus mu k mg divided by m will equal a. So I think the push force was 4 newtons minus 0.1 for the coefficient of kinetic friction times 2 for the mass times about 10 for the gravitational field divided by 2 equals a. And I think that ends up being 1 meters per second squared. I think. Is it 1? Alright, so now we've got an incline. So I'm going to just sketch the picture over here. So here's our incline, and the block is sitting on the incline, and maybe we've given it a little shove to get it going. Maybe we've given a little shove down the incline, but you know, it can be like moving. Those are my like it's going symbols. This is our 30-degree angle. And it's a rough surface, so if you want to give it some little scribble lines to remind yourself that it's rough, then there you go. Not always going to be drawn like with little scribbles, but you know, you can do it for now. Okay, so we're going to Freebody Diagram. I'm going to recreate my little object at the same angle there. I'm going to make the x-axis the parallel to the inclined plane, and the y-axis perpendicular to the inclined plane, so that my weight force is straight down. And the weight force truly acts at the center of mass, which is why I always kind of draw the weight starting from the center of the object. The normal force is from the surface onto the object, so a lot of times I'll draw the normal force starting from that little bottom of the surface there. And this one has friction on it, so I might even draw the force of friction coming from the bottom of the object there. Now, why did I draw the force of kinetic friction going up the incline? Yeah, because my little like run-in little things show that it's like maybe going this way. Oh, that would be slowing down, wouldn't it? Powell, you made it look dumb. Okay, but it's going down the incline. The initial velocity. How about that? Okay, so the force of kinetic friction would have to be opposite of the motion. And then this is our angle theta. So now I'm going to sum the forces in the new x direction. And this is why rotating the axis is so beautiful, because now we will have the acceleration in one dimension. If I didn't rotate the axis, you'd have like this x-axis this way and an acceleration that way. And so you'd have an acceleration that has both x and y components. Ugh. That is not easy to solve. So by rotating my axis, I've actually made this so much easier. Alright, so then in the x direction, if I let down be positive, then that means that mg sine theta, the weight component along the incline, minus the force of friction kinetic would equal ma. And in the y direction, now it's not hopping up off the incline or sinking into the incline, so the net force in the y direction is balanced in 0. So that means that the normal force that's pointing away from the incline minus the weight component that points into the incline is equal to 0. So let's see. F sub g means m times g sine theta minus the force of friction is mu kinetic times force normal. But force normal in this case is not just mg. It's the force of gravity in that y direction, a component. So it's mg times cosine theta. So be careful. The normal force is absolutely not always equal to the weight. Sometimes it's equal to a component of the weight or something else. All right, equals ma over here. So, now I can take this guy right here and dump it back in over here. Boop, boop, boop. So then I'll have mg sine theta minus mu k mg cos theta equals ma. What am I looking for? The acceleration. Very good. So, what can I do now?
Divide by mass.
Oh, we can't divide by mass everywhere. So, if I double the mass of the object, what happens to the acceleration? It would be the same. Does the mass matter?